to the next stage. And okay, we can start now.
Okay, so good afternoon, good morning, jurors, and also everyone. So I'm Jaden Wong from in Hong Kong, and I'm going to present problem 11, which is the swim of chromometer. So the problem is as follows: to pass linearly polarized white light through a column of sugar solution, when the transmitted light is observed through a polarizer, it may appear colored. Rotate the polarizer, and the transmitted light may change. So then we have left two tasks here. So the first task is that we should construct such a sweep chromometer, and secondly, we must optimize for the narrowest light wavelength bandwidth. So here are some of the parameters that we've changed: the rotation of polarizer, the concentration of sugar, the length of tube, and also the type of sugar. And then for the measurements, we take the total irradiance, the value of the total irradiance, and also the output spectrum, and also the bandwidth. So what does it mean by a bandwidth? So the definition is called the full width half maximum. So basically, for this peak, for example, for this peak, you see the difference between half of the peak intensity, the difference in the bandwidth that it passes, the wavelength passes will be the everything track. So that is called the bandwidth. So then moving on to the theory, the qualitative explanation. For a linear polarized white light, it can be divided into the RCP and also the LCP, and yeah, basically it's like this. So then, for sugars, they actually exert a form of chirality. Because the sugar has a chiral centers, this means that the carbons are bonded to 4 different substitute groups. This means that there will be an asymmetric structure of sugar, as you can see here. Yeah, as you can see, the red dots are the chiral centers. So during the transmission, the oscillating electric field of the light interacts with the electron cloud inside of the sugar solution. And the electron clouds oscillate at the same frequency, but out of phase as the incoming light because of inertia and also the inductance, right? So as you can see here, these are some this is an animation. And then for the asymmetricity of the electron cloud, because the whole sugar molecule is actually asymmetric. So this means that the amplitude of absorption of LCP and RCP is different, and therefore it will intuitively create a helical spiral with randomness. For example, I don't know if I can say, yeah. And then for the rotation of light, for example, glucose, there's 2 types. So the RCP will actually align with the preferred direction of the electron cloud movement, while the RCP interacts with the electrons much more. Because the interaction has a phase lag, this means that the phase velocity for the LCP, the left rotating light, will be slower, while the RCP, which is the right rotating light, which is in the opposite direction, will have a higher phase velocity. And because light is basically the combination of RCP and LCP, if there's a difference in the phase velocity, this means that the light will turn right, as in there's a right helix, right rotating helix of light, and therefore the polarization decays. So this is basically how there will be a rotation of light. And I would also like to say that within the qualitative theory, that the different wavelengths actually twist light differently. Because the sugar electrons have a natural absorption range in the UV range, as you can see here, which is experimental data. And then the electrons respond more vigorously to shorter wavelengths because of resonance, right? And therefore, the overall effect is that the shorter wavelengths will rotate light more because the effects the asymmetricity effect will be much stronger. And then, therefore, when we apply a polarizer on top of the sugar solution, you can see that the transmitted spectrum will change because when you rotate the polarizer, the selected light wavelength will change, and therefore the output color will change as well. So moving on to the quantitative theory. So there's firstly the induced electrical dipole. That induced electrical dipole is basically this, put into 2 parts. The first part is achiral, and the second part I'll explain it later. So the induced electric dipole moment of a molecule when interacting with a light EM wave is here, as we've said in the quantitative theory. And therefore, this is the effect of the B field, which is the chiral part. As you can see here, there's a right-handed helix in which the electron travels because of the asymmetricity. Yeah. And therefore, using this Rosenfeld equation, we can actually Rosenfeld scalar, which sums up all the possible electron transition states, we can arrive at this formula, which is the rotational strength of the sugar. And then we use Orca and delta, which are two most popular quantum chemistry apps, and we can actually calculate the optical rotation because out of the coordinates, and and which possible states the electrons are. So we basically solve a lot of Schrodinger's equations. Then therefore we can find out this natural absorption and also how the rotation, how strong is the rotation. So we then apply the Lorentz transformation. So then so we basically sum up the electrical field, and then we put into this formula, and we combine with the relative permittivity, and we found the Clausius-Mostetti equation. And then moving on from that, we do a little bit of rearrangement, and therefore then we apply the Taylor expansion, and therefore what it basically does, the physical meaning of what we are doing is that we're trying to model how there was an increase in the sugar in the solution. It will basically create a sort of Hawking effect, because it will interact with each other and the electric field will be summed up. So then we apply the Biot's law, we substitute the previous equation in, and then we substitute the Rosenfeld scalar, and then we basically do a little bit of conversion, and therefore we can find out this equation, which is basically the rotation. We find the rotation angle out of this function of the Drude coefficient. The Drude coefficient is different for different sugar, and therefore we calculated it using the Open and Dalton again, and we can therefore find the different calculated, and we compare the theory, and there's an error in the results. And then to find out the wavelength that actually comes out because of the second polarizer on top, we can actually use the Mahler's law, which shows the wavelength, how it differs when you have two different polarizers. I'll show the experimental setup later. And the PLW law here, it basically corrects for the absorbance of sugar inside, and that will be experimentally fixed, that's here. And then to calculate the bandwidth, we basically take the derivative. We take the derivative of the rotational angle, and therefore we can find out this will be the final mass equation of our bandwidth. So therefore, here are some of the hypotheses on the parameters. We believe that the tube length and also the concentration will have an inverse effect, and then the measured wavelength will have measured wavelength as in the light that is measured at a certain point, I'll explain it later, will be a pseudo-cubic situation. And we also predict that the fructose will be the strongest type of sugar. Yet, because of this, because you multiply the specific rotational constant with the maximum concentration possible, right? Yeah. And so moving on to the experiment, here is our experimental setup. So there's actually two linear polarizers, because we are asked to pass linear polarized white light through the first one. This is our Ceylon arc lamp. We'll explain why it's important later. And then here is a flat DPC2, which is where the sugar solution goes. And then this is the experimental setup. One laser is used to ensure that it's vertically downwards, and then so here is the spectrum of the xenon arc lamp that we have used. We can see that it's basically uniform on top. This is important because we need to show how if there's a flat top, we can make meaningful conclusions out of it. So moving on to the analysis. So firstly, we compared the theory with the experiment. The experiment will be the red dotted line here, and then the theory will be the yellow line. We believe that there's a good theory experimental agreement. And then the first thing we varied was the measured wavelength. That is like for a certain wavelength. So we rotate the polarizer to different angles first. And then for each angle, we find the peaks and recorded the corresponding SWHM. And we put all the data into the graph below, and we see that the spectral bandwidth basically increases as the peak increases as well. So moving on. So if we change the rotation angle, basically it shifts the whole spectrum lengthwards. So this, you can see that there's no theta term here. So how does it come up? It comes up with the Mahler's law. The Mahler's law, you can see that there's a theta here. It basically changes this term. So as you can see here, if you shift the angle, it doesn't change the bandwidth. Yeah, it doesn't change the bandwidth. And here is basically a spectrogram showing how the intensity will change when you shift the angle, as you can see on the y-axis here. And then moving on, we varied the length of the tube, and we found out that if we increase the length, the bandwidth basically converges to a very small value. And then moving on, we linearize it and to find the R square, and we find it to be a good theoretical experimental agreement as well. And then for fructose, we did the same. And then we move on to the next parameter, which is the concentration. We could we think that it's inverse, and as you can see here, it's actually inverse. So, and this, we also change the concentration of fructose in order to find an exact strength as well. And then we mix vary the type of sugar, which is at the same concentration, because different concentration have different saturations, right? So this means that, as you can see here, maltose basically has for the same concentration, maltose has the most strongest effect of the rotation observed. So that means the spectral bandwidth will be smaller for maltose. And then moving on, for a larger concentration, we basically observe that maltose is also the strongest. However, at the maximum concentration, as in the saturation of the sugar, we find that fructose actually has the strongest rotation, because as you can see in the previous slide, fructose has the highest saturation. So this means that when you times it with a specific rotational constant, it will be the largest. Yeah. And then therefore, because of this, we find the optimized wavelength, optimized activation. Sorry. And this is, we use the fructose, we use the maximum concentration, and also we use the maximum length of the paradox, which is 15 pm. So therefore, we can find out that our optimized activation is at 413 nanometers. If we consider this peak, it will be 6 nanometers. While for the other end of the visible spectrum, it will be 680 nm, and it will be basically 18 nm. So therefore, moving on, we also find out how can we characterize the monochromatic effects, which is we call it on a CIE graph. And basically, we see that it's basically white, because it's like the resultant thing is basically white. As you can see here, it basically shows every spectrum. So when you combine it together, it will be white. So that is all our interesting phenomenon today. We have found out how the activation can be calculated and how do we optimize it and build one correct setup. Thank you so much.
Okay, thank you very much. Straight away we move to questions from the opponent.
Okay, so my first question is that can your equations in the explanation of the phenomenon explain why the symmetric molecule rotate light?
The what?
Yes or no, can the equations explain why a symmetric molecule doesn't rotate light?
Yeah, it does, because the
we'll get into that later in the discussion. And did you consider varying the solvent?
No, we only use water. But we vary a lot of sugar. Yeah.
Okay, and did you consider changing the temperature maybe in your experiment?
We believe that it has a small effect. I'll show it to you later.
Okay, thank you. And where did you get the data on absorption from?
So we actually calculated using organ data, which are suites on my computer that uses Schrodinger's equation.
But the absorption coefficient is from the literature.
No, I didn't use the literature. I started from ground up.
So you measured it?
No, I didn't measure. I calculated from the theory.
Okay, thank you. And how did you measure, or I didn't get from the literature, the rotation coefficient? So for example, in your rotation
this is basically the way, because I use this to I use these two apps to calculate using the Schrodinger's. Yeah.
Okay, thank you. And how did you interpret the wording monochromatic?
Oh, so monochromatic, I think it's well, I think there's two definitions. I use the definition in which there's the smallest bandwidth, because that's basically in the common scale.
Okay, thank you. And how long did you wait after making the sugar solutions before?
12 hours to account for the mutual relation.
Okay, yeah, thank you. Very much. And what kind of spectrometer was used in your experiment?
Oh, so it's basically this spectrometer. I didn't connect it to a large spectrometer. This is basically a handheld one. Yeah.
Okay, thank you. You have preparation time, reporting consent. Okay, if we could get people quieting down and have the opposition.
Hello everyone, I'm Nicolas from Hungary, and I'm going to be attending problem number 11 this week. When it comes to the theory, the reporter explained the phenomenon with the curative sugar, and it was based on the interaction with the electron field and the AC electricity, which is basically what curative means. And the theory that he used for his model was based on Morse's law, induced electrical dipoles were taken into account. Also, for the explanation of the phenomenon, he also used the Rosenfeld scalar to explain the rotator strength. And for his model, which he created the simulation, Taylor expansion, which he included Biot's law in. And yes, the simulation was created, as I said earlier. For the experiments, he used a professional spectrometer to measure the wavelength and density. He had very, very high on the solution. He also varied the concentration, the type of sugar used. Also looked at peaks at different wavelengths. And he compared the theory with the experiment. There was a very good match with the experiment, and also compared different sugars. So I think that's was well done. And yeah, the explanation of the was, I think, overall quite well done, used the right equations. However, I think maybe it was a bit too complicated, and it could have been explained more clearly. I would also want to talk about that in the discussion. For the quantitative theory, again, maybe more simple theory could also accurately describe this rotation. However, overall it was great, and as we could see, it described the phenomenon quite well, so I agree with that after all. And the optimization was well done. Many parameters were considered. However, for example, varying the solvent, which I think can be interesting when it comes to pure solvent, or varying the temperature, which wasn't accounted for. And also he verified his theory by experiment, which did match. So the strengths of the report were overall that there were many types of sugar investigated, there was an intuitive explanation based on asymmetry, there were many insightful graphs, and also optimization for the narrowest bandwidth was done, which is the task. And however, there are some possible ways to improve. For example, considering more parameters, as I stated earlier, temperature and solvent are, I think, other relevant things. Also, varying the light source could be interesting. However, I like that he used the homogeneous light, which I think is important in this case. And also, that would be more focused on setup. For example, he didn't have the polarizer characteristics, and most applies for perfect polarizers. And I'm not sure, obviously, polarizers are somewhat imperfect. And also he didn't tell us how he did his measurements. For example, it shouldn't be done in a dark room, but I like that the setup was black. So overall, the explanation of the phenomenon stood as being more clear, but the explanation of the optimization was done pretty well. Thank you for your attention. I would like to invite the reporter to the stage.
Okay,
And
switch to time.
Yeah. So
so first of all, I want to start with the explanation of the phenomenon part. So can you go to the slide where you have the Rosenfeld equation? Maybe. Or actually, I just wanted to ask. So how do you explain that a symmetric molecule doesn't rotate like? Can you?
This is the thing we were discussing. But the way it works is basically how you see that there's two terms here. Wait, I don't know where my mouse goes. Wait, I'll just pretend like this. Okay, so for this you can see that there's actually two terms. So the first term here, the for this is the polarized. This is the electric field contributed from the solvent. So maybe water or alcohol or whatever. And therefore that part will be affected. But that doesn't really make it rotate because it's aligned. That part, the beta that part is the Rosenthal scalar. So Rosenthal scalar is what rotates the, as I've mentioned, how it rotates the electron path to a spiral. Yeah.
Okay, I understand. And you have this rotary, this equation, which if I understand well, is a rotatory strength.
Yeah.
And it's the, so there are two vectors, the scalar, the electric and magnetic dipole solution moment,
Yes.
right? That's what it describes. But, so...
No, what I'm just trying to say here is that because those two equate a non-zero dot product. So
they have to be zero and then there is no rotation.
If
right?
if it's zero, then there's no rotation.
But how do you explain that they are zero for a symmetric molecule?
No, it's just because there's a change in defect and then it's not perfectly perpendicular. So therefore they will have a non-zero dot product.
So for symmetric molecules, these vectors are perpendicular. That's what you're saying.
If consider like if there's a pure water, then obviously then there will be no rotation.
Yeah, but how do you explain that? Why are they perpendicular? Do you have a qualitative explanation?
Yes, I think it's here. So as you can see here, this is one of my chiral. So you can see that when the vertical axis, the y one, is basically how the second part, this part, the green one is how the chirality is explained.
I understand.
Yeah.
You're talking about the circular polarized.
Yeah.
I was asking about the vectors in that equation. So for
It's chiral is like this because there's no changing field. So it's basically planar. So you don't think. Yeah.
Thank you. I don't think you actually answered my question clearly because I asked about that Rosenfeld's equation, which gives a rotative strength, and I asked why is it zero? So why are the vectors perpendicular in a symmetric molecule? For which I didn't get an answer, and I think if we investigate this further, it could be actually the whole rotation part could be explained more clearly without complex models, because I don't think it's actually sufficient.
What do you think would be a kind of suggestion then? Because I think it's perfect enough. Because as you can see here,
for example,
yeah.
in my opinion, if you're looking at the symmetric molecule, for example, a Wolf's molecule, and the two vectors are perpendicular, so this one and this is the electric dipole moment and the magnetic dipole moment. They have to be perpendicular because this is what ensures the mirror symmetry of the molecule.
Yeah.
So if I actually flip it, or reflect it, along the symmetry axis, we will get the vectors we will get the exact same orientation of the vectors because the magnetic dipole moment is a pseudo vector, meaning that it flips signs on the mirror reflection.
Yeah.
So even if I reflect it, it will the electric dipole moment will point in the same direction, and this will also. So, but yes, so that's all. I think that this way it could have been explained a bit more clearly, especially since you brought up the rotators.
Okay, sure. But I think you will agree that there's two kinds of this, right?
But let's go to the next topic, anyways. So what as I was asking about is, did you consider, or why didn't you consider using chiral solvents? Do you think it would be a good further improvement to also investigate?
Okay, I believe that using a chiral solvent may have use, but note that sugar does not really dissolve well in chiral solvent. So
okay, I actually agree with you because you can't really find a chiral solvent that dissolves sugar very well. So yeah, we agree on that. And what about varying temperature?
Oh, varying temperature. So we didn't really vary the temperature because we believe it's very hard to keep the temperature very constant inside the but otherwise we believe that the effect of the temperature is very small because I quoted this from literature. So you can see that it's 0.00037 times the temperature minus 20 because all my experiments were done in 20 degrees under a controlled environment. And then I also turned off the light, but sorry I didn't show you the experiment because obviously I turned off the light, right? And then
okay, thank you. Thank you for clarifying that.
Because of that, I also measured the extinction ratio.
Okay.
So
let's get back to temperature. So what you're using is like a linear equation.
Yes,
it's used for small temperature changes.
Yes.
But yeah, you didn't investigate it, which I actually understand that it's not the most efficient, especially because it's very hard to keep the temperature constant and
Yeah,
things like
to
that.
keep it, I also, for the light source, I didn't turn it on for a very long time because otherwise it would be heating of the polarizer.
Yes, that's actually very thoughtful. What about, did you measure your polarizer characteristics that they actually follow Moses' law as ideal polarizers?
I think the fact that like I think we measured the extinction ratio, that is because like it's not a perfect polarizer, right?
Yes, of course.
So definitely we characterize it in. So I think that the theory experiment also shows that there's like it basically follows the mass law. If that's what.
Yeah, but I think it would be sufficient to just measure the polarizer characteristics. So without the sugar solution, just see how much light is transmitted when at different
orientations. Yeah, we basically did that. This is how we measure.
Also that. Okay. So you actually, and did you apply that in the theory?
No, because we found out that the extinction ratio is 1 to 30,000.
So they're almost ideal polarizers.
Yeah, they're almost ideal.
Okay, then I think we clarify this. Although I think it would have been actually sufficient to maybe explain or talk about it in the report as well. But no, I understand it. So that is definitely. And what I wanted to talk about as well. So how did you measure the rotation coefficients? For example, slide 22, I think, or I'm not quite sure, but where you had the equations on the rotation of the 20 something, maybe 25.
25.
Yeah, I think 25.
This one.
Yeah, so you, here for example, lambda naught, can you, like...
Yeah, lambda naught is the resonance wave temperature.
Yeah. Did you get that from literature or did you?
No, we calculated ourselves as well.
But how did you calculate it?
No, because the fact is that OTA basically generates like because the way I did it is that I modeled the thing and I calculated the lowest energy like the lowest energy state, the coordinates of different atoms, and basically the software then solve for the natural frequency of it.
But don't you think that it would have been easier to measure the optical rotation in your experiment from that from Bill's study? You have the specific rotation there, and then you kind of fit or like do a trend line for your measurements, and that's how you get the constants.
Well, because yeah, I think it would be a verification of our
more effective
yeah,
method.
I agree.
But I think your method is also good, but this would be a bit more effective or easier, so maybe that would make the understanding of this whole thing easier. And also, you measured absorption as well, was it wavelength dependent?
Absorption, as seen from
or
here.
Or like Beer-Lomberg's law explains the transmittance.
Yeah, so basically here you can see that from the experimental data, you see that there's some variance in the absorbance between in higher wavelengths.
But that can affect the actual width of the peak. So did you consider that in your theory?
Yeah, it's so as you can see here, there's like the experiment having I say so you can see that there's some discrepancy here, and I believe it's because of that we didn't take it because the experimental it will be splitting the experimental data with the experimental data basically.
Well, I think that's actually valid in the theory that based on your experimental data you also put in the equation, Beer-Lomberg equation, and that way you actually account for the wavelength dependency of absorption to find the actual nearest peak. And also, for example, didn't we consider interpreting one parameter as such that it only considers one peak? So.
Oh yeah, we did as well. So there's another.
Okay, it goes on for time and requirement.
Okay, so I would like to summarize our discussion. Overall, I think it was a very insightful discussion where we touched important topics. For example, the explanation of the phenomenon, which I think it was a bit too complicated, the way the reporter explained it, and also didn't quite have a clear answer on why a symmetric molecule doesn't rotate light, which I think is a very interesting part of this physics problem. And also we talked about using chiral solvents, which we agreed on that it's very hard to get a chiral solvent that actually dissolves sugar. And then we discussed the polarizer characteristics, which the reporter actually measured. I think it would have been nice to see in the report as well. And that talk about absorption and that it would be a very good further improvement if actually include the wavelength dependence of absorption in the simulation. And also another implementation of with only one.
Okay, stopping there. Thank you. We move on to questions from the reviewer.
Okay, hello, my name is Anna, and first I would like you to go to slide 50. I would like to ask the reporter whether you think that this spectrum, which is optimized in your opinion, is monochromatic.
Well, I believe that I've done the task that is to optimize for the narrowest wavelength.
Is this spectrum monochromatic, yes or no?
No, in a sense.
What does the opponent think?
I also think it's
Okay, I think that the problem statement was we should monochromize.
But no, it doesn't.
Then I would like to ask whether when you increase the concentration and height, the peaks only decrease in pH. Am I correct? No, please go back to that slide.
50, right?
Yes.
Yeah.
If we change concentration and the length of solution and we higher them, do the peaks get thinner or larger?
Thinner, of course. That's how
So
we
your
optimize.
optimization is in infinite length and the maximum solubility?
Yeah, obviously, but we can't do that.
Okay, so it's not possible to optimize it in your way.
Well, if we have a longer tube and then
Okay.
few more solution, then
Then I would like to ask, what were the inputs into your atom model?
in my
You modeled atom and electrons
Yeah,
vibrating.
so-
What were the inputs into this simulation?
so you have a rough model of the shape of the like the atom, and you give the molecular formula. That's it.
Okay.
And also the weight
Can
is all
you please go to slide 37?
Where is that?
We see proportionality here in your equation. Does the proportionality come from your theoretical model? Why isn't it a specific equation and only proportionality on the right top?
So we just simplified it for the to show that the
Okay.
trend. Yeah.
And on slide 29 or also 36?
29.
29, for example, yeah.
29. Yeah.
Oh, sorry, 36. Is this line fitted?
Which line?
The theoretical line.
No, one of the theory line.
And the next slide, 37. Is this line only a fit, or is this your theoretical model?
This is the theoretical model. And
Okay.
it cut off at 650 because the light intensity goes up.
Okay, then I would like to ask whether the two epimers, the alpha and beta form of the sugar,
Yeah.
how they are accounted for in your modeling of the atom.
Oh,
how
so-
do you know the epimer ratio?
So there's mutual rotation. So you actually know the ratio from the
From the literature or somewhere? And you
not
know
the
both
literature.
of these
Not
both
the
of these epimers?
Huh?
And you know both of these epimers? You
Yeah,
know
we
not
also
both of them?
we have.
Okay, thank you. I think that's wonderful. And for the opponent, you asked about this time that it's needed to leave the solution to sit down. Were you linking on the mutual rotation
Yes,
process?
that's what I was referring to.
Okay, thank you. I think the 12 hours was sufficient.
Yeah,
That's all from me. Thank you.
Okay, you have preparation time. Opponent can sit down.
No, this is
quickly. Okay, we need to start.
Yeah. Okay, my name is Anna, and this will be the review for problem number 11, sweet monochromator. And I would like to pinpoint this, that we were supposed to construct a sweet monochromator and optimize for the narrowest wavelength bandwidth. And I actually think that the reporter misunderstood the problem statement, since it said that yes, there should be a narrowest light wavelength bandwidth, but not only that, it should be monochromatic. The light that he obtained was actually white, with many peaks. And I think that was like the main problem of the presentation. However, there are still some nice parts, so I would like to go into that. First of all, I would like to praise the complex theoretical model that he set, where he modeled atoms and calculated the vibrating frequency of electrons, which is important for understanding of the phenomena. And I think this was really nice. Then I liked it for quantifying the width of the big used PVHM, which is the most used method. I really liked that in his apparatus the source of light had really even distribution of the wavelengths in the visible spectrum. And I liked the qualitative explanation of each part. However, I think it was quite difficult to follow and was lacking visuals that would make it easier for a person who never worked with this before understand it. I think that he didn't monochromize, and that even when looking at his approach, it would actually give us the solution that an optimization would be in infinite length and the maximal possible concentration in the given solvent. And that was also not really done, therefore I don't see any optimization and I don't see any monochromatization. Then there were also some questionable theory versus experiment graphs where they weren't matching all that good, even with this complex model, and deviations were not really explained all that well. And also the inputs into the theory were quite unclear, and it was quite a complex model, so I would maybe like more insight into this. For the opponent, I really liked the questions, not much their prioritization, but like the content was really good. I really liked that she asked about the monochromatization. Also the varying temperature, it has an effect not that big, but it was interesting. I like that she asked about the mutuation and the different absorption bands, and also the symmetricity of the molecules. What I didn't like all that much was that we didn't get any clarifying questions about the theory, and she also really pushed the varying of solvent, which I think would only make this problem even more problematic, so I think water is sufficient in this case. For her speech, I like that she pointed out the lack of qualitative explanation and that it was unclear, and they also said about absorption bands, and I really think that she has deep physical insight into this phenomenon, and it was really visible from the speech but also in the discussion. However, I didn't like that she didn't have a problem with the fact that the transmitted light is actually white in some and not monochromized. For the discussion, first thing they discussed was the symmetricity of the molecule, and this was quite a lot of time spent on this, I think first 4 minutes, which I think is quite a lot, since the entire problem is about antisymmetric molecules. I understand that she wanted to gain some intuition about how the theory works, but I think that this could have been lower on the priority list. Then they discussed the dependency on the solvent and the temperature, where opponent suggested changing these parameters, and I agree with the reporter that this is not really all that important, and changing the length and concentration is the more important thing. Then they discussed the Mell's law and whether it was experimentally verified and if the polarizers are actually of high quality, which I liked that the reporter said is basically by his measurement it was almost ideal, which I think is great in terms of his experimental apparatus, which was really nice and had quite a lot of potential. And then they discussed the rotation coefficient and how was it obtained, and it was said that he experimentally measured optical rotation, which I think is fine, but was kind of lost inside of the presentation because of the rather poor science communication. Then, to sum up the discussion, what I think about it is that I think it had a bad prioritization, and the question about the optimization was at the very end of the discussion, life is 5 seconds, and I think this should be on top of the priority, but I like that the opponent had many other opinions. For the points missed out, I would first of all say that this was quite a misunderstood problem, but other things would be more about the sense communication of the inputs to simulation, how it accounted for bit rotation, and I would also suggest having a better visual qualitative explanation of different phenomenon, because this is quite a complex list of things you have to understand to be able to understand the
Okay,
situation.
thank you very much. We go to closing remarks from the reporter.
Okay, so basically, I think that we have had a very interesting discussion today. So firstly, me and the host has discussed on how the Rosenfeld scalar and how there are actually two different terms which shows one is a Haro and the other is Haro. And then and then we pretty much had like a conversation on how the optimization works, and also a little bit about the experimental cell and what are some like temperature effect on it as well, and also like if the polarizers are idealized or not. And then I would like to focus this concluding remark firstly on a summary of my report, which is basically we have verified different parameters, and then we definitely find out the optimization, which is the length goes to the length increases, the concentration increases, and also like the type of sugar used to treat fructose. And however, there was one interesting standpoint that comes out of the reviewer that says it's not a monochromator. However, I would like to have another argument on that, because there's two ways to go with this problem. The first way is my way of doing this, and the second way I actually investigated as well. It's called the CIE relativity. So it's basically mapping your eyes, like how you visualize light onto how you visualize light basically. So then the monochromatic definition would be how pure the light is. However, if you make the light more pure, this does not actually optimize the narrowest wavelength. While it actually creates a huge peak, and you cannot really it creates a huge peak here in the visible wavelength, and then this is not actually optimized. So that approach is basically self-contradictory in itself. So that's why we did not really consider that case except on the further analysis. However, therefore, we believe that our way of doing this is actually optimizes the FWHM, and therefore we also constructed a sweet monochromator that works and we successfully have a good theory and experimental prediction. Thank you.
Okay, thank you. And moving on for questions from the jury. Yes, please.
Could you show me that graph says you got signal and what you measure? You know, one of those graphs. There's several of those type of graphs. Well, that's fine. That one's fine.
This one?
No, next one, the one with the Wiggers spectrum.
This
yeah,
one?
yeah.
Okay.
What is it? Actually, I don't understand what you did, and if this is something that coming from the xenon light and you are building the monochromator, what happened in those dip?
Oh, so it's basically the Maler's law, like it predicts for the two polarizers. It's like, for example, we have two
No, I'm
polarizers.
asking simple question.
Yeah.
What are you measuring it at right at that dip? If, for example, if your source after you linearize it, let's say your sugar column did something, filtering out the spectrum colors, right? So if that particular comes out, what you measure? What do you measure? Right at the tip. If that color of spectrum is right at the wavelength, what are you measuring?
There's no light of that wavelength.
So that means your monochromator failure in that particular color.
No, but you can rotate the polarizer of the second polarizer so you can shift the peak to the leftwards. So if
but that's the different wavelengths. So right at that particular wavelength, that means your monochromator doesn't measure anything, right?
Yeah, but I can rotate it and then you can measure it.
Okay, I think it's as long as we can one question.
Yeah. Okay.
Another question?
Opponent, I saw in the slides you suggested to have a concentration gradient.
Yes, it was on one of the slides. So if I don't think it's that relevant, but it's worth mentioning. So if the sugar solution
it's not relevant, you say, so what's relevant at the end?
So if but can I say what I mean by that? So if the sugar solution is left for long in the tube, there can be some concentration gradients that is more concentrated on the bottom than the top, but that can kind of cause some deviation in the intensity measurement because light scatters differently then. But it's not the most relevant, but should be.
So it's just a column that, I mean,
Yes, that's what I meant.
Certainly.
To the reporter, you computed, you made these simulations,
Yeah.
electronic simulations, and you compared the results to literature values.
Yeah.
What kind of literature values were they? Were those also simulated ones or
No, the literature values were taken from a paper.
But what was it taken from an experimental paper or from a theoretical paper?
I think it was an experimental paper.
Any other questions?
Can you maybe show the table again? So that,
No, this is this one. So the literature.
Okay, any final question? We will go to compiling remarks. Okay, thank you. You can sit down and we'll go to compiling remarks.